Okay, guys, so I want you to go ahead and make 2 pages to put in your binders. One of them will be the Cornell notes for today, but also, just for clarity, I want you to have another paper that goes under the classwork section in your binder, and it needs to include all the questions from the Do Now, as well as the questions from the Pair Up. I noticed they were multiple choice, so you don't have to do all the answer choices, but please do copy down the questions and also copy down the summary. And then at the end of those 3 things, I need you to copy into classwork. Also go ahead and copy in what I'm circling right here, which is the homework assignment, which we will do in class, of course, if we have any time at all. And if we don't, I may need to have you take that home for a bit, but we're gonna try to use all that time in class to get all that work done. All right, so so definitely copy down your Do Now, Pair Up, summary, and the homework assignment into the classwork section of your binder. And we'll jump right into the lesson now. Okay, so my mini lesson is basically a discussion of stability versus instability. We all know people who can be stable or unstable in terms of their personality, but we can also apply some of that same understanding of the definition of instability to the atom itself. So here are some fun facts. In general, the elements that are most likely to have little psychotic breakdowns or emit radiation are the larger elements. Now, if you're wondering how you can define large, you should be thinking anything over an atomic number of 83. So I believe that means that bismuth would be the last radioactive element, or the last element that's not radioactive. Okay, so then also there's a ratio of neutrons to protons that's nice. So if the ratio is nearly 1 to 1, and that's only for certain elements 1 to 20. So I believe element number 1 is hydrogen, and I believe element number 20 is calcium. So if you're within that range of elements, then you can use the ratio 1 to 1, and that's 1 proton to 1 neutron. And that would make it stable. And then if that ratio is not 1 to 1, we would call it unstable. So for instance, if I ask you, is nitrogen-14 stable or unstable, I want you to use that ratio rule and show your work, here's what I would do. I'm going to ask you to pause the video while I write in my answer. You should be thinking about, just look at the question and see if you can figure out what the neutron to proton ratio is there, and see if you think it's stable. All right, I'll fill you in with what I've figured out so far. Firstly, is the element in question, nitrogen, is it in the range of element 1 to element 20? It is. Nitrogen is element number 7, so it's within this range, so that means I can use my 1 to 1 rule. So the neutron to proton ratio needs to be 1 to 1. I went ahead and wrote out my isotope like this. It says nitrogen-14 up here, but the 14 is going to be a mass number. And then I did get a number 7 for the atomic number, and I know that because the element is nitrogen. So nitrogen is element number 7. I got that from the periodic table. So using the 14 and the 7, I can say that the number of protons is definitely 7. And the number of neutrons is going to be the mass number minus the atomic number, which is 14 minus 7, which in this case is 7. So 7 to 7 is the same thing as 1 to 1. So I'm going to say that the neutron to proton ratio checks out as well. I think we've had enough information to say that nitrogen-14 is stable, because 7 to 7 is 1 to 1. Moving on. So part 2, there is more about this story because there's more to the radioactive particles themselves. When something is unstable, we don't actually call it psychotic, guys. We call it radioactive. That's a key word here. Radioactive or radioisotope. So this is more like something, it's like describing something. I guess we could say it's an adjective. And a radioisotope is more like a noun. It's the thing itself. So I'll go with adjective. and noun. You may want to look up if I have my grammar straight, because I don't actually know if I used adjective and noun correctly. But this means that the nucleus breaks down spontaneously. And here's another vocab word for you guys. Spontaneously means all of a sudden. It doesn't need help from something else. So, to backtrack, we have something that's unstable. We might call it radioactive, we might call it a radioisotope, but that means that the nucleus breaks down by itself spontaneously. And when those little nuclei do break down, they emit all different kinds of particles. And each one of those different kinds of particles is going to be called decay. It's a decay particle. The trick is to remember that the nucleus contains more than just the three major subatomic particles, which were protons, neutrons, and electrons. As it turns out, those particles have smaller parts, which have even smaller parts. So that's going to bring us to what are all those parts? Table O, as you may remember, is a great way to keep track of all those parts. I'm just going to highlight it right there. So the three decay types from Table O that we might consider normal would be things that look like protons, and things that look like neutrons, and things that look like electrons. So I went off the beaten path a little bit here with the symbols I chose, but I chose this symbol to represent proton. It is one option in addition to the P. I used this symbol to represent neutron, which is my typical symbol, and I used this one to represent the electron because sometimes people would use a Greek letter B, which is beta. All right, so we have some other mystery particles that are on this table as well. Right now I've only covered protons, neutrons, and electrons. So we have others, and those would include alphas, gammas, although it's not technically a particle, and positrons. Don't forget beta. Beta could be considered one of those extra particles as well because, let's just put it this way. Electrons should not be coming out of the nucleus. They orbit the nucleus, so if an electron is coming out of the nucleus, then there's something deeper going on. We're going to use the law of conservation, which is something we practiced in, I believe, last night's lesson to help us find out. So firstly, what is the law of conservation? So what I wrote in was that matter, energy, and charge cannot be created or destroyed. So if you were looking at a nuclear reaction equation that was showing the emission of alpha particles, what would you notice about the element that was in decay? So I'm just going to call your attention to it one more time. We have this nucleus. It's decaying via alpha decay. And I know that because I'm looking over on the right-hand side and I see that alpha particle, so I know it's alpha decay. But what would I notice about the changes in this isotope as it transforms into this isotope as a result of losing this particle? So you're always going to find the same types of stuff when you're looking at a nucleus that's undergoing alpha decay. In terms of atomic number, what you will notice is that it'll drop from a number like 88 to a number like 86. And basically that means that it's going to have a reduction in atomic number of 2. And then that also means that the number of protons, of course, has reduced by 2. Now, neither of these things should be very confusing because if you look at the alpha particle itself, it has an atomic number of 2. It has 2 protons in it. So it makes sense that this should go down by 2 because this guy has 2. And it's saying that it's really law of conservation because 86 plus 2 is 88. We're showing that matter cannot be created or destroyed or charged. Now, in terms of the number of neutrons, it's a bit harder. There's 2 ways to solve this, and I think the easiest way is to check out the fact that the alpha particle has a mass of 4 and it has 2 protons. That means it also has 2 neutrons. I'm doing 4 minus 2 is 2 neutrons. So if the alpha particle has 2 neutrons, then the number of neutrons in the radium isotope has decreased by 2 when it turns into radon-222. So I'm going to go ahead and say decreased by 2. But the other way to think about that one is to just think that if you're going from 226 to 222, that's a drop of 4 mass particles. And you know that 2 of those 4 mass particles are protons because you see 88 to 86. So that's 2 protons that are lost, and that would be included in the mass. So the 4 masses that were lost, if 2 of them are protons, then that means 2 of them must be neutrons. And then lastly, how was the mass number? How did that change? Just look at it directly, 226 to 222, that's a decrease in 4. So all of these things that I'm circling in red are hallmarks of alpha decay that you should know, you should be really familiar with, and you can cite at a moment's notice. All right, so the other 2 mystery decay types are called beta and positron. I have a little bit of math I can show you that can help explain their origin. So to start with, I'm going to zoom in just a bit. And we'll fill in just do a little bit of algebra. All right, so one of the decay modes, either beta or positron, begins with this neutron, and the other one begins with a proton. And what you're seeing here overall is that a neutron is transforming into a proton. It's also going to do something else on the other side. And then here you're seeing a proton that transforms into a neutron, and you'll see just a little bit of extra something coming out on the other side. Now, with some pretty basic algebra skills, we can figure out what those things are. The law of conservation says that matter cannot be created, nor can it be destroyed. So if we have a mass of 1 neutron on the left, a mass of 1 in this neutron, then that means on the right-hand side, all the masses added together have to be 1. And I see that I already have 1 in this proton. So that means to me that particle X, which up until now has no identity, also has a mass of 0. Now the neutron has a charge of 0, but the proton has a charge of 1. Now, when I add up these 2 charges for the particles on the right, they have to equal the charge of this guy on the left. And that means they have to add up to 0. So the number that you can add to a 1 that'll make it turn into a 0 is a -1. Now, that's a huge difference between -1 and +1, so make sure you keep track. But overall, what I'm suggesting here is that a neutron can turn into a proton if it releases some particle who has a mass of 0 and a charge of -1. So the only particle I can think of whose mass is 0 and whose charge is -1 is a beta particle. So you could write it like that, or you could write it like that. All right, so let's fill in the blanks here. A neutron decays into a proton and releases a beta in the process. All right, so there's my information. A neutron decays into a proton and releases a beta in the process. All right, let's do one more. Here we have a proton decaying into a neutron and releasing something else in the process. Let's see what that is. So the mass of 1 on the left is matched by a mass of 1 on the right, so that means the mass of that particle has to be 0. The charge of 1 on the left is it's not matched by a charge of 1 on the right. So this number plus this number have to equal 1. And if you just call out some algebra skills, you're going to get +1. So the particle that has those properties of mass of 0, charge of +1, is a positron, which you could use that symbol, or you could use that one. So fill in some info here. It looks like a proton decays into a neutron and releases a positron in the process. Okay, so where we're at so far is that we're in the last little bit of the video, and we're going to, just in this section, we're going to do a quick part 3, which is to predict the decay mode. Use the law of conservation to help you with this. I'm going to ask you to do this in 2 steps. I'll tell you the steps now, but I'm going to have you pause the video in between. First step is I want you to use law of conservation and algebra to figure out the properties of that particle, the properties of this particle, and the properties of this particle in terms of its mass and its charge for each. And then figure out its identity and write the identity in, and then we'll talk about decay modes in a second. So pause the video and figure out what are each of these particles. Use the law of conservation and algebra. Okay, so I zoomed in a bit, but I also was able to determine that the mass of this particle would be 0 because 14 plus 0 equals 14. The mass of this particle would be 0 because 37 plus 0 equals 37. And the mass of this particle must be 4 because 216 plus 4 equals 220. As for the charges, I know the charge of this particle has to be -1 because 7 minus 1 is 6. For this particle, the charge has to be +1 because 18 plus 1 is 19. And for the charge of this particle, the charge has to be +2 because 85 plus 2 equals 87. And that also gives me the identities without much trouble. For instance, the identity of the first particle, that has to be a beta. The identity of the second particle has to be a positron. And the identity of the fourth particle has to be an alpha. I'm going to zoom out a bit. The decay mode, remember from our previous lesson, is just described by the kind of particle that's being spit out. So in the first one, this particle that's being spit out appears to be a beta particle. So I'm going to call this one beta decay. And no fancy dancing around the bush there. I'm going to call this one positron decay because I see a positron being spit out of the nucleus. So again, this beta particle makes this beta decay, this positron makes it positron decay, and this alpha particle is going to make the answer to that alpha decay. All right, so we're coming up to the very end of this. I just want to give you guys a quick little overview of Table N. Table N is probably new to you at this point. It is super wonderful. Table N has the answers to all of life's questions, or at least some of the region's questions. So let's start. I hope that you have a good time with it. So sometimes you'll be asked to predict the specific type of nuclear decay particle released by certain radioisotopes of elements. Table N is perfect for this because otherwise you might be flummoxed by this question. What is the decay mode of an iron-53 nuclide? It's awfully specific. No one can memorize that much information. So when you're asked for the decay mode of an iron-53 nuclide, make a little alarm go off in your brain that you've been asked something very specific, so please check a reference table. Table N is that table. So when you go to iron-53, you're going to look for it. You'll scan down the table, and I think I found it right here, Fe53, that's iron. It also has the name over here if you're looking for it, and it seems that it has a decay mode of positron. So I'll write that in a second. Secondly, what's the charge of the particles emitted by nitrogen-16? So if I go down the table to nitrogen-16, looking for it, found it. Here's nitrogen-16. The question says, what's the charge of the particles? So nitrogen-16, here's beta particle. The charge, of course, would be -1, which is for beta. Now we have, what's the decay mode of plutonium-239? So come down here to plutonium-239. Plutonium-239 is right there. It's got an alpha particle. So that means that the specific kind of decay is going to be alpha decay. Moving forward, what's the mass of the particle released by the decaying nucleus of a technetium-99 atom? Technetium-99, right there. And it has a particle that it's releasing, and that is a beta particle. The mass on that, it would be the same as an electron. So there's two answers here. The Regents' answer, they want you to say 0 AMU. But there is, there are textbooks that would accept 1/1836 AMU, which is the mass of an electron and would be very similar to the mass of a beta. All right, so which radioactive nuclide has a half-life? And no, you do not need to know what this is yet. Which radioactive nuclide has a half-life of 1599 years, but it also has an alpha decay mode? All right, so alpha decay modes, here's half-life, here's one, alpha decay mode, and its half-life is not 1599, so go back down. Alpha, half-life is not 1599. Oh, here it is, alpha, and the half-life is 1599. That's radium-226. So there we are. Last question is, what is the most popular decay mode for the heaviest nuclides? So if you go down here to the heavy nuclides, the 200 guys, the 239, 226, 222, 232, 233, 235, 238, I'll go ahead and circle them. Those ones in the 200s. Look, guys, each one of them has alpha decay. So whenever you're just asked offhandedly about something like this, radium-226, if you're in the 200s, that is almost always alpha decay. All right, so we've reached the end of this lecture. I do want you to, in your classwork section, there's 4 things you need for today. You should have already copied down the do now, but now please copy down the pair up. Just the questions will suffice. You don't need to copy down all the answer choices. It can be frustrating. So the question will suffice, and I'll put these questions up tomorrow so you can see the answer choices, and copy down the summary. So that's 3 things. Copy down the do now, copy down the pair up, copy down the summary. Fourthly, I want you to go back to that beginning of the video and copy down the homework assignment, and we'll do that, the book work, we'll do that in class tomorrow as well. It was lovely. I hope that your notes went well. Have a good night.